So, good morning and welcome to this session of the InterPore2020. And it's my pleasure to welcome our invited speaker, Stéphane Zaleski. My name is Bernhard Kroos from RWTH Aachen University. I'm a research scientist with a background in experiments, and I've been asked to moderate this session. So welcome again, and we're hoping for a very fruitful and very exciting conference for us and also for the organizing group. This is definitely a new experience, and I would like to thank the organizers for their efforts and for setting up this conference in this way. Before starting the session, I would like to remind you of the behavior expectations. Please, if you're not speaking, keep your microphone on mute. If you have a question, please type ** hand up into the chat box in the WOVA to be called on, and the Zoom chat should be disabled. Filming or other recording is prohibited. And the session will be recorded for InterPore, which includes the video and voice recording. The recording, questions and answers, and chat in WOVA will be accessible for 1 week after the end of the conference. Now, it is my pleasure to introduce to you Stéphane Zaleski of Sorbonne University. Stéphane is a professor at Sorbonne University who, after his doctorate at the École Normale Supérieure in Paris and early years at the physics laboratory of the INS, joined the mechanics group at Université Pierre et Marie Curie, Paris 6. He investigates numerical methods for multi-phase flow with applications to atomization, cavitation, porous media flow, boiling, hydrometallurgy, contact lines, and droplet impact, including several variants of the volume of fluid methods, the diffuse interface method, and molecular dynamics. Stéphane has written several computer codes for the simulation of two-phase flow, including the Paris simulator, and recently he has applied these techniques to the study of COVID-19 airborne transmission by micron-sized droplets. He's associate editor of the Journal of Computational Physics and of Computers and Fluids. He's also the recipient of the European Research Council Award 2020-25 and a member of the Institut Universitaire de France for the 2020-25 period. Now, after this introduction, I would like to ask Stéphane to start his presentation entitled Contact Line Motion Using the Volume of Fluid Method.
Oh, thank you, Bernard, for the wonderful introduction. And I would like especially to thank the organizers of InterPore to invite me at this conference. It's a real pleasure. I have been working on porous media flow for a while. Here is a picture from one of the simulations we performed with Igor Bondino at Total and Thomas Arufat and others. And so there is a session on this kind of flow, on the numerical simulation of multi-phase flow in porous media, with the main organizer being Martin Blunt. And session that is active sessions at this conference, and you know, we just are quite advanced now in this area. I'm citing many other groups. And have becoming a mature science, you can have some geometrical representation of the porous media and run a flow through it, but of the dynamics, the capillary about that, and I will emphasize that there are two essential ingredients to do that. One is to be able to solve the NavierStokes equations of multi-phase flow, and the second is to be able to deal with these simulation methods with contact line dynamics. And so I'll briefly remind you of the NavierStokes equations. They are quite standard, and this is not really the point here. The point here, you have to add boundary conditions, and the boundary conditions are represented here. One of them I've not written is you specify an angle at the boundary. Usually this is the equilibrium angle, the same angle you would have with a motionless droplet. And the second is a boundary conditions for the velocity, and that is much more tricky. Usually on a solid, you learn in school that you have to have zero velocity. But if you have zero velocity, the contact line cannot move. And so, as I said in the abstract, not even Herakles could think a solid, because you would need infinite force to make the contact line move. Now, once you introduce slip, it removes this singularity that was discussed by Huh and Scriven, and now the contact line can move. So this is a good, well-posed model of so-called Navier slip, and I will discuss that as we go on. From the NavierStokes point of view, we can use all sorts of grids, and many people have used finite elements, for example, for unstructured grids. We try to gain high speed of computation by using so-called octrees, where you refine cubes or squares in a hierarchical way. There are many codes doing that, including Jerry's and Basilisk, written by Stéphane Poppinet. And we combine this with volume of fluid, so you can see this kind of piecewise linear reconstruction going on here with these small discontinuities. And this is combined with methods to compute curvature and hence capillarity. So I will go back to that later. So again, many codes can do that, including many things done with open form, and actually many variants of open form. There are many variants that can deal with capillarity, surface tension, and contact lines. If you now flow in a porous media, one of the important characteristics is the formation of thin films. This is, of course, difficult because you have to resolve the thin films. You need small grid sizes, but it's also difficult because the dynamics are complicated. Because of the singularity in the motion of the contact lines, the formation of the thin films is very difficult to predict. Often, as you refine the grid, you see films that form while they should not have formed, or the reverse. So this is something I will also discuss in what follows. So I would like to make these ideas more precise by explaining how we deal with contact lines with volume of fluid. And first I have to explain how we deal with motion of the interface with volume of fluid. So once we have represented the interface by these segments, we advance the points A and B on the two faces into the points A prime and B prime, depending on the velocities here on these faces. And when you have a solid boundary near a contact line, this is good because it allows the contact line to move, even though on the solid, perhaps this does not move. This is what is called an implicit slip. A lot of methods have so-called implicit slip. The alternative is to allow for explicit slip, as I said before, and this is probably more sound because it removes the difficulty of the contact line motion. But I will come back to that a little later. There are still some difficulties with that. One nice feature of the Jerry's code by Stéphane Poppinet is that it's a layered propagation. So in fact, instead of one velocities, you have n velocities on the faces of the cell. So you can move the interface while sort of rotating it. And here you see an example of the rotation of the interface in the volume of fluid method in Jerry. So you have the green line and the red lines are two manners of of propagating the interface, and the red line is the default representation in Jerris, and you see that in the default, the rotation is much cleaner than in the green case. So this is also probably good near the contact line. So now I've talked a lot about volume of fluid, but I have not yet said how we move the contact line. So let's see that. In step one, we have the equilibrium angle, or the what we call sometimes the numerical angle in the first cell, theta delta. We reconstruct the interface with that. And then in the first step, we extrapolate this reconstruction to the next cell. So now we have theta delta in the next cell, the first cell inside the solid. And then we use this extrapolation to compute so-called heights. And it's these heights which are then differentiated to get the curvature. And so we can do this with so-called vertical heights or horizontal heights, or width, W. An important thing is that currently in our Basilisk code, only the widths are extrapolated, but while in Jerris we can also extrapolate the heights. So this method works very well, at least for a capillary number larger than 10 to the minus 5. Here are some example tests with Jerris, with capillary, actually even 10 to the minus 5 in this case works nicely, and a contact angle of 30 degrees. We're going to test this on a slightly more complicated geometry. This is work which was done with Thomas Fulana, and is the curtain coating configuration where you have a downward flow of liquid, and that is meant to coat a moving solid here. And so as the solid moves to the right, you have here an advancing contact line, and the formation of a thin film here, the coating film. And you have two velocities. You have the downward velocity here, and you have the horizontal velocity here. So you have two parameters. And the interesting thing is that the result really depends on both parameters, not just the velocity of the contact line, but also the sort of impetus or strength with which you push the fluid downwards. And if you go too fast, if you try to coat too fast, if you are too much in a hurry, because you want an industrial process that goes fast, for example, this contact line will become unstable, and the air here in white will create little bubbles that will destroy the nice well-coated film. So there is a kind of transition. And what we want to do is to predict when this transition happens. And so here is an example of the simulations with Basilisk. So you see the octree grid, which is progressively refined. You see the downward flow here on the, between these purple lines. The colors correspond to the vorticity. So you see you have a vortex here that has formed on the left in the air, which is not extremely important. If you zoom in this region, you'll see the foot and the neighborhood of the contact line. So we have to zoom many times to be finally able to see the grid near the contact line. So you see that finally we were able to resolve a nice uniform wedge. What is amazing is that in this case, we took a slip length of 10 microns, and nevertheless, we can resolve this slip length by going down to a grid size of 1 micron. So the domain was about 1 centimeter. So we are able to reduce the grid size by a factor of 10,000. And this is essentially due to the octree character. And so in this case, the thing behaves well, and we have convergence near second order of the position of the contact line. And if we now compare it to the experiments that were performed by Blake in 1999 and Shikmurzaev, the results are not so convincing in this case. We don't reproduce the results of Blake, and in fact, the slip length is the best fit. And reassuringly, or not, the other simulations by Liu give the same qualitative behavior, but also fail to precisely reproduce the experiments. And so this raises a number of issues. If you go to another set of experiments by Marston and Hawkins, here the best fit for the contact and the slip length is 450 nanometers. Now this is a much bigger slip length, so it's easier to do the simulations, and our simulations agree with those of Liu, Carvalho, and Kumar. But for the experiments, it's again only qualitative. So what are the surprising facts here? The relatively large values of the slip length, the disagreement with the experiments, and this leads us and many others to believe that we need better contact line models. But in order to make progress, we also have to face two main difficulties or conundrums. The first one is that if we go down to slip lengths of the order of 0.1 nanometer or 1 nanometer, it will be extremely difficult in practice. We will not be able to do larger samples of porous media than 1 micron, which is probably not what you want to do. And the second conundrum is that if we also move very slowly, like with a small capillary number or a small Laplace number, so that's small capillary number is slow, a small Laplace number is rather viscous flow, then the simulations become difficult again. Let me show you an example. This is an example at small capillary number and Laplace number, and you have these strange velocities near the contact line. So these are called spurious currents, and we have huge spurious currents here. We have worked on that with the group of Hamdi Chelepi, the group of Martin Blunt, and with Arthur Moncarter from Total. We've compared very many methods. It's very difficult to get rid of these spurious currents. So the possible improvements is a better contact line model, and also improve the numerical methods at small capillary and Laplace numbers. The two issues are linked because in order to try to improve the first issue, we resort to molecular dynamics, which involves then very small Laplace numbers. So this is an example of molecular dynamic simulations with all the parameters are given here. They're mostly air and water on silica. And this is a view of the numerical simulation. There is a talk by Uji Slassis and others at this conference a little later. So I will skip the details, but I will show you with molecular dynamics, we compare with volume of fluid, and we have this, this straight line variation, or this sloped variation of the angle here, which is reproduced by volume of fluid, but volume of fluid does not work near the boundaries. What does it mean? Well, this slow variation points to the hydrodynamic theory of Cox and Voinov. So I don't want to show too many equations in that talk, but this is the essential equations coming from the Cox and Voinov theory. That is, the angle depends logarithmically on the distance to the contact line. So we designed an experiment to test this theory, and I'll go over this quickly because there is a finite time. So this is a withdrawing plate experiment, and you have a region of variation of the angle here. And in this region, if you don't have a very resolved slip length, the shear diverges, which is the root of the logarithmic variation in the Cox-Voinov theory. And so in this setup, we have set the following physics: gravity, surface tension, viscosity, and a well-defined contact angle. But we still don't have an ideal contact microscopic model for the contact line. And we also use implicit slip in this case, not explicit slip. So you see here again some simulations. They are similar to the previous ones. And we look at for each static angle and grid size, we determine a critical capillary number at which the film stops forming. In contradiction with the previous, in opposition to the previous case, this is a receding contact line. And so the critical capillary number now is much smaller than in previous case. In the previous case, it was an advancing contact line for which the critical capillary number can be as large as 60. Here we have a small critical capillary number. So you see here all the capillary numbers that we obtained for the various angles and the various grid sizes. And you see that the critical capillary number depends on grid size here. This is an example of the non-convergence of these methods when you don't resolve the slip length. And we explain this divergence by the existence of this intermediate region, which is the logarithmic region of Cox and Voinov. So we reproduced the Cox and Voynov theory again, and we determined this coefficient lambda here, which determines the interior length scale of the Cox-Voynov theory. So this is a little bit technical, bear with me. We check the existence of the logarithmic region in these slides, and we should have the correct slope. It's approximately verified. And we finally can predict the critical capillary number using the Cox-Voynov theory. We use then the existence of this logarithmic region to compensate for the singularity by being able to use a numerical microscopic contact angle that depends on the grid size. So theta delta, the numerical contact angle, is made to depend on the grid size delta. So there are a number of people who do that. I suggested this with Sharaf Kami, and then it was taken over by Legendre and Maglio in a very nice paper. And what Legendre and Maglio did, they studied a spreading droplet, as many other authors did, and they have shown that as when you use this compensation method and you reduce the grid size, and then you obtain consistent results. Now you get convergence when you reduce the grid size, which you couldn't have before. Unfortunately, this method for compensating for the grid size reduction or the singularity has not yet been implemented in actual simulations of very complex geometries of porous media, but it is the basis for, I believe, future simulations of contact lines in porous media. So thank you very much.
Okay, Stéphane, that's the end of your presentation?
Yes. I end with the perspective. Yes, that's the end.
Okay, thank you very much for keeping in time. So we have about 10 minutes now for questions from the audience. There are no pre-recorded questions because this presentation was not issued ahead of time. Now, the question to the host: are there any chat contributions? Do we have any questions from the audience?
I think you need to check the chat. I didn't check the chat.
Okay, well, let me see if I can check the chat. I have the participants, but I do not have a chat window here right now. I have the number of participants.
I see that Shervin Bagheri has raised his hand.
Who?
Shervin Bagheri has raised his hand.
Please,
on Zoom, you can see that someone raised his hand.
Yes, please, could you ask your questions in the chat function? And then I would like Bernard to go to Hoover to see the chat. You need to have the Hoover open and Zoom in order to see the questions. You won't see the questions in Zoom, Bernard. Stéphane, do you see the questions in Zoom, in Hoover? I'm sorry, you see?
I see, in the chat, there are no questions. There is one person who raised his hand, who is Shervin Bagheri.
Yes, I have one question here. This question comes from, the question says, can you comment on multiphase? It is coming from Hadi Hajibegi. Can you comment on multiphase flow modeling, please?
Oh, I have to ask a counter question. You mean a comment on averaging the multiphase flow, averaging for the interfaces to have an average saturation? Is that what you mean, Haji? Okay,
I have to wait now for Hadi's reply on WOVA.
I can give you a tentative reply if, before we have Hadi's reply.
He's not on the.
Okay, the question.
Let me see the attendee. Okay, maybe I can open him here.
If you model and if you average a multiphase flow using Darcy type models with with saturations, then what happens, the only way you can represent what happens is by making the permeabilities dependent on the capillary number. And of course the contact angle. Then this is a larger scale effort, and other groups are trying to do that numerically, but at present, the groups I work with have not been doing that.
Okay.
Do you see other questions?
Does any, well, Hadi, I do not get a reply here. Hadi, did this answer your question? I'm inviting other questions, preferably via the WOWA.
I see questions on WOWA, Bernard.
Okay, let me see.
Is lambda related to the material? I don't know who asked this question, but it was question,
okay,
question by C. Suo. And
okay.
Yes, it's an excellent question. Lambda absolutely characterizes the material. Lambda characterizes the interaction of the fluids with the surface, so it also characterizes the material. It could, for example, and it also characterizes the roughness of the interface, yes. And it's extremely difficult to measure, where there are no known measurements of it.
Okay, so apparently, Stéphane, you have a better response from WOWA. I'm yes. Stuck here with this.
I have a question. How would you rate the computational, this question by Stefan Berg. How would you rate the computational cost of implementing this method? The answer is that it's not very costly, because you only need to implement it in the neighborhood of the contact line on the solid surface. So the various methods for the contact line that I'm using are not costly in terms of computational time. So that's all the questions I have for the moment. But
okay,
could you allow Shervin to say something, to open his microphone, because he apparently raised his hand, so I suppose he had a question.
So who was that? I didn't get the name.
Shervin Bagheri. He asked a question in Zoom. He raised his hand in Zoom.
Let me see.
Maybe he has not his hands raised anymore, because maybe you can raise your hand and then it goes down. Yes, I see a raised hand. I'm going to allow Shervin to talk.
Yes, yes, please do so. I
so
cannot.
Shervin, you can talk now. Shervin, you hear me? I think I don't see him anymore in the. Yes, I see him.
Shervin? I think, Caroline, you have to allow him to talk, because I cannot.
I can't see him in the attendee list, I have to say.
Here it says it's not available because Shervin is using an older version of Zoom.
Ah.
You need to promote, okay, we have to promote him to a panelist.
No, I cannot do that. I cannot promote him because he entered from Hoover. You cannot, from Hoover, you cannot do that.
Okay, so we have to ask him to ask a question via Hoover?
Yes, he needs to do that in Hoover.
Can you hear me?
Yes, I can hear you.
This is Majid Hassanizadeh.
Hello, Majid.
Hi, Stefan. Very nice talk. Thank you. I just actually, first of all, I want to say there are a couple of more questions on chat. I can see that. But for example, Amir Raouf is saying, nice talk. Can you comment on range of density and viscosity difference that can be handled?
Okay. Excellent question. Excellent question. There is, in principle, in these methods, there is no difference on the ranges of viscosities and densities, but in practice, a lot of the actual physical experiments are done with one phase that is air, and the other phase is water or some kind of oil. So we have much more experience with gas, liquid situations than with liquid-liquid situations, at least from what I can see. So that I'm taking this opportunity for a call for experiments. We need a lot of good experiments to make progress on these issues.
Actually, related to that, I was going to comment that we have done a few micromodel experiments where we can, with reasonable resolution, see the movement of interfaces and contact lines associated with that. And some of them are, and these are indeed with different densities and viscosities. So
sorry, I have to stop this because we're running out of time. I just saw that the question asked by Sherwin Barreri has appeared on WOVA. So please answer it and continue your communication offline.
Okay.
I have now to stop this session. First of all, I would like to thank the speaker very much for this interesting and thought-provoking presentation. And I would like to thank the attendees. And again, please contact Stéphane, use the WOVA app to ask further questions and to continue this, this discussion. Thank you very much to all of you. And I close this session now, and the host is going to take over. Thank you very much.
Hi, Bernard.
Yes.
You shared your screen. I think now we all like leave the session. Okay.
Okay. Yes, please. Let's leave the session. And thank you very much for taking care of this.
Yeah. Thank you. Bye.